and welcome to this session for TYBSc students in the subject of physics for semester 6, course code PYD106, course titled Nuclear Physics. This unit 6B is about nuclear models, especially focusing on the nuclear shell model. The name of this module is Main Assumptions of the Single Particle Shell Model. I am Benedict Suarez from St. Xavier's College, Mapsa, Goa. The outline of this is first the introduction, followed by the nuclear shell model and the details about the assumptions of the nuclear shell model. At the end of this course, the student will be able to understand the stability of nuclei. They should be able to appreciate the nuclear shell model and understand the main assumptions of the nuclear shell model. The existence of magic numbers in case of nuclei suggests the possibility of a shell model for the nucleus. Magic numbers are the number of protons and neutrons necessary to form closed shells in the nucleus. Nuclei with proton number or neutron number or both proton and neutron number equal to magic numbers 2, 8, 20, 28, 50, 82 and 126 are found to be extremely stable. The shell model for the nucleus was developed by Maria Joubert-Meyer and independently by Hexel, Jensen and Swiss. So these three scientists were working together and Maria Joubert-Meyer was working independently for this model. The shell model is more or less similar to that for the atom except for some differences. The shells in the atomic structure are filled by particles of only one type, that is electrons, while the shells in the nuclear structure are filled with two types of particles, protons and neutrons. In the atomic structure, the electronic shells are due to a central field of force because of the Coulomb force of attraction. While in the nuclear structure, the central field of force which gives rise to the shells consists of two different types of potential. A constant potential which gives rise to the potential well model for the nucleus and a potential which is oscillatory in character. The main assumptions of the single particle shell model. Each nucleon in the nucleus moves in its orbit within the nucleus independently of all other nucleons. Each nucleon is regarded as an independent particle. The mean free path of the nucleons in the nucleus is large compared with the nuclear dimension. The orbit is determined by a potential energy function V of R, which represents the average effect of all interactions with other nucleons and is the same for each particle. Each nucleon moves in a field created by the other nucleons, which is assumed to be the same for all nucleons. The potential of this field is assumed to be static and spherically symmetric. The interaction between nucleons is considered to be a small perturbation on the interaction between a nucleon and the potential field. Nucleons obeys the Pauli's exclusion principle, the effect of which leads to considerable weakening of the interactions between the nucleons. The energy of a nucleon inside the nucleus is given by the values of 4 quantum numbers. First, quantum number n, which is called the principal quantum number. Second one, quantum number L, which is the orbital angular momentum quantum number L. The third one, quantum number J, which is the total angular momentum quantum number J. Mj is the fourth quantum number, which is the total magnetic angular momentum quantum number Mj. There is strong spin-orbit coupling for each individual nucleon, due to which each nucleon energy level splits into 2 sub-levels, and this spin-orbit coupling is responsible for obtaining higher order magic number. The references are Nuclear Physics by Irving Kaplan by Narusa Publishing House, Atomic and Nuclear Physics by A.B. Gupta and D. Ghosh by Books and Allied Publishers, Nuclear Physics by A.V. Namjoshi, J.A. Rao, C.S. Asgaonkar and A.D. Palekar by Sheth Publishers, Perspectives of Modern Physics by Arthur Beiser by McGraw-Hill Publishers, Introduction to Modern Physics by F.K. Richmeyer, E.H. Kennard, J.N. Cooper by McGraw-Hill Publishers, Nuclear Physics by S.B. Patel by New Age International Publishers, and Nuclear Physics by K. Langovan by MJP Publishers. Thank you very much.